How do you measure the size of a nucleus? If you were to measure anything, you would first probably reach for a ruler, a device that has a scale that you can compare to the object you are measuring and read off a value. If it's really big, you need a big ruler. If it's small, you need a small ruler. But what if the object you were trying to measure was so small that you couldn't use a ruler? That's the problem we face when we are trying to measure the size of a nucleus. Nuclei are the centres of atoms and so small that very few other things are smaller than them. You can split them, you can combine them, but what can you do when you want to measure them? What is a ruler? It's a device that you put next to an object that has a scale on it. You look at the scale on the ruler to see how big an object is. But what if you're trying to measure that object in the dark? You would need to bring in an outside light source to see the object and the scale. What if you couldn't get close to the object to measure it? You would have to look at it from a distance and hold the ruler close to you to see the scale. In these two situations, you are better seeing what you need to do to measure something. You need to see the object you are measuring and also the scale you are comparing it to. In one of the most famous experiments of all time, Ernest Rutherford did just that with the atom. The result that most people know about was the determination of the structure of the atom, but the result we will talk about here is the determination of the size of that structure. Rutherford discovered that an atom is a small, hard, positively charged centre surrounded by electrons in mostly empty space. In order to determine this, Rutherford had to establish the approximate size of the centre of the atom, and so he created a method to discover the size of the nucleus. Rutherford's experiment involved firing positively charged alpha particles at a gold leaf target and measuring the angle and intensity of the alpha particles after they were reflected, deflected, or passed straight through the gold leaf. Rutherford's experiment showed that most of the alpha particles simply travelled straight through the gold leaf, proving that most of the atom was empty space. However, by firing a beam of alpha particles perpendicular to the plane of the gold leaf and measuring the angles of the scattered alpha particles from the nucleus, we can plot the trajectories back and determine the size of the nucleus. If we know the velocity of an alpha particle moving towards the gold nucleus and that alpha particle is scattered directly back at the emitter, we can measure the velocity of this alpha particle and so determine how close this alpha particle came to the gold nucleus. As the alpha particle moves towards the nucleus, it is repelled by the positive charge of the nucleus. This repulsion turns the kinetic energy, half mass times velocity squared, of the alpha particle into potential energy, 1 over 4 pi epsilon naught q, 1 times q2 over r. Once this kinetic energy has been turned into potential energy, the alpha particle is pushed back towards the emitter. If it is moved directly back, we do not have to worry about angles and cosines. All the kinetic energy is turned to potential, and all the potential is turned back to kinetic again. Because we know the potential equation, and we know the kinetic equation, we can make them equal to each other, just as the kinetic and potential energies are equal, and rearrange to give an equation that will tell us the distance to the gold nucleus and the alpha particle were when they were closest. R equals q1 q2 over 4 pi epsilon naught all divided by 1s mv squared. We get the charge of the alpha particle and gold nucleus from the proton number times 1.9 by 10 to the minus 19. We control the initial velocity, the initial kinetic energy, of the alpha particle. We know the mass of the helium nucleus and epsilon, so can work out the smallest distance these two particles were apart. For an alpha particle with kinetic energy of 5 mega electron volts, the closest the alpha particle gets to the gold nucleus is 5 by 10 to the minus 14 meters. The radius must be smaller than this.